yesterday we had the first class in a series of 4 on the idea of using sparsity to design learning algorithms, and in particular regularization algorithms. So the idea is that somewhat we start to explore what it means to be, what it means to be sparse for a solution, and why this could be a good idea. So what we did yesterday is that we began by just somewhat recalling the standard Tikhonov regularization with L2 norms, and the extension we consider in special case of square loss, including, for example, the iterative regularization, also called early stopping, or truncated singular value decomposition. And the key things we did yesterday is somewhat reviewing the idea of regularization for least squares as filtering. Okay, so this is the first thing we did yesterday. So if you remember here, the idea is that we filter by writing each vector on a special basis. You remember which one is the basis that somewhat arises naturally when you're doing things like, say, ridge regression or gradient descent. Again? The eigenvectors of what? Absolutely, the eigenvectors of what? Yeah, so there is some data matrix X. And in fact, if you want to talk about eigenvectors, really you should take something like this. Or you can just take something like this, but then you have to talk about the singular vectors. Okay, you have this basis and you want to use that. That's perfectly fine. And we recall that in the statistical terms, that basis, so the VI, okay, there are some, the VI in our D, say, that are associated to this matrix are not just any vectors, right? They have a name. You remember, how do you usually call the eigenvector or the singular vector of the design matrix, of the data matrix? They're just the principal components, okay? So this was the one observation we did yesterday. And the second observation is that all the regularization I've seen until yesterday for least squares was based on a special kind of low-pass filtering. That it was actually looking not only at this eigenvector, but also at the order induced by the eigenvalues. And remember, roughly speaking, what was the filtering doing? It was based on an assumption. Let's write a vector that we try to find on the eigenbasis. And then let's do what?
Order the eigenvalues.
Say it again?
Order the eigenvalues.
Yeah, so you order the components so that, say, you have big eigenvalues first and small eigenvalues later. And then what do you do? How do you filter? You keep the components that correspond to high eigenvalues, and you view them as kind of low frequencies, okay, so something regular. And then the components that correspond to small eigenvalues, you throw away. So this, in filtering theory, this is what is called, according to these analogies, what you can think of as a low-pass filter. You let low frequency come in, and you decrease high frequency. So that's a perfectly fine idea. We discovered that we can look at regularization from this perspective. We said yesterday that the shortcoming of this idea is that well, maybe you can remember. What is the shortcoming of this idea? When will it is that this algorithm will not work? You start, and the first thing you do is that you throw away components that correspond to small eigenvalues. Well, clearly, if the function you're looking for a lot of information on the components corresponding to small eigenvalues, this sounds like a definitely bad idea, okay? And in that case, rather than filtering through low pass, we can do some kind of nonlinear filtering that basically says, if you remember, this is the picture I was drawing yesterday. So here you have the big, and here you have the small eigenvalues. And let's say if you have just a couple of components and then a bunch of small spurious components that you can think of as noise, then basically the idea is that rather than make a cut like this, which say I let pass the components corresponding to big eigenvalues, the idea is that you want to do some kind of cut like this. So that is, say, all the coefficients that are higher than a threshold, I keep. Everything below the threshold, I set equal to 0. Okay? So clearly this is a good idea, not if my function, my vector, has big components corresponding to small eigenvalues, to big eigenvalues, but if essentially some components are much bigger than something else, okay? And in particular, if only few components are different from 0, and all other components are equal to 0, okay? This situation is what we call sparse vector, okay? This is a sparse vector over some basis. So you take a vector, you consider its components over a basis, and if only few of these components, so some of these components are different from 0, we say that this vector is sparse. So the idea of making this kind of cuts is based on the idea that the vectors we're looking at is sparse over a given basis. Okay, so this is how somewhat sparsity appeared in our discussion yesterday. And the key, and this is special to, the discussion we did yesterday was special to SVD. Okay, it was special to the case where here the basis was really the basis based by an SVD, where you have big eigenvalues, small eigenvalues. And indeed, this notion of sparsity is conditioned to a choice of a basis. Okay, as we recalled yesterday, while the general theory, well, whatever, let's leave this alone. This notion is conditioned to a choice of a basis, okay? And so what we tried to do yesterday is try to think, okay, what do and when I say basis, I don't really mean basis in a strict sense, but some kind of dictionary of functions. And so after this small introduction yesterday, we say, okay, let's move on, and let's try to see how you can generalize this idea of doing something like this to more general scenarios, okay? So let me just rewrite a couple of equations. So yesterday what we saw is that the solution based on data that would implement a filter of that kind is something that looks like this. So if you remember, usually the previous regularization would act only on the eigenvalues or the singular values, whereas this one actually acts on y itself. It says, let me look at the component. If it's big, I let it live. If it's small, I throw it away. This map here is what is called it's a map. In this case, you just have a number. And basically what it does is that it says, if this, it will be useful today to write it this way. If this number is big, I decrease it a little bit. If the number is small, I set it equal to 0. If this number is big in magnitude but negative, then I decrease it a little bit. So the shape of this is something like this. Okay? Between minus lambda and lambda, it is 0. When it's bigger than lambda, it's a line that intercepts the y-axis in minus lambda, and similar here. Okay? And we ended up saying that this function here can be proved, and this is essentially an exercise that you're going to do, to be the argmin of a least square problem penalized not with the L1, but with the not with L2, but with the L1 norm of the coefficient. Okay? So this function here can be shown to be exactly the solution to this problem. Okay? This is an exercise. It's not too hard to prove. We're essentially going to redo it today. So the one observation here is this looks almost like what we usually do. If you put up there a square, all you get is just a square norm. Okay? If you were to put here a 2, then this would just be the L2 norm. And the choice of a basis doesn't matter. Okay? for any basis, you can just have an equivalent description of the norm. The moment you actually remove these two, what you get is what you typically call the L1 norm. And this notation is a bit misleading because this norm really depends on the basis you choose. Okay? And again, just this is important, this is a very important point. You can imagine that you have a vector which is sparse on a basis. Say it has only the first component different from 0. And then you just rotate the basis lat. You do a small change of basis. And all of a sudden, now you need a lot of vectors to extract that one component. Okay? So the notion of sparsity is conditioned to a choice of a basis. Okay? So this is an important point. So in this set of lectures, we are not going to discuss how you choose the basis, okay, or the dictionary. We're going to try to see what you do once you have the basis and the dictionary. This is very similar to what we've done so far, where we said, okay, let me show you what you can do when you have a kernel. It's even worse in a sense, because here, perhaps through this dependence, the dependence on the choice of the dictionary is even stronger, okay? You cannot rotate anything. You just have to stick to that. At some point, this discussion is going to come along, okay? As I promised towards the end of the course, you know, the last few lectures on data representation, learning data representation, to some extent are really going to be about how do you choose the dictionary, how do you learn a dictionary. So let's postpone the discussion, okay? For now, what we want to discuss is, okay, fair enough. So this is what happens if I pick this basis, okay? More generally, let's try to see what happens when you choose any other basis. And what we were left with, and yesterday we do this reasoning a little bit, so the idea is okay, let me just write a function of this form over some very generic dictionary phi 1, phi p of functions, okay? So instead of the singular vectors, I want to take something else. What? I don't know. You gave it to me, okay? The problem gave it to me. We spent some time thinking of what is the dictionary. So similar to what was before, what does it mean for a function to be sparse? Well, same as before, right? Before I had to put here the singular vectors. Here, just take this guy. What does it mean that the function is sparse? That these coefficients, most of these coefficients, hopefully, are actually equal to 0. And now what we want to do, if we want to try to extend this reasoning without perhaps losing the filtering perspective, but keeping this idea of sparsity, the idea is that perhaps what we could do is to try to derive some regularization principle. Notice that here this L1 was coming from this filtering perspective, okay? Here we kind of reintroduced, when you move to a new dictionary, which is not the SVD, that reasoning doesn't hold anymore. It just served as a motivation in a case that we know how to manage. In the case of a general dictionary, the way we describe this is essentially by saying, okay, I need some notation, okay? Let me first do it like this. Let's look at the least square. Let me put here lambda so that we really see that it depends on the vector of coefficients. Okay, so something in the spirit of this seems to be the following functional. Okay? In this functional here, we have a least square term, and then we have this L1 norm, which is the L1 norm of the coefficients. Okay? Let's massage this a little bit. Okay? Let's try to write it in that form so that we can carry on with the vector notation. I claim that this is essentially something that looks like this. Can you tell me how? Can you give me a matrix X so that I can just write this in this vector notation? So I would like to know how the matrix X hat that I have to put in. So X hat will not be the data matrix. it will be something like there exists a matrix that is not the data matrix that I can put there so that I can write that error term. Yeah, so let's define some matrix X, let's call it tilde just to avoid confusing, and tell me what is an entry or what is a column, whatever you want. Let's be slightly more general. So let's say phi I xj. This would be the ith row because I want n of them. And then this will be the jth column. Okay? If you do this, now because of this expression, you can see that you just get something that looks like that. Correct? Okay? So this is the reason why. Is this clear? Because we have this expression, if we define a matrix X tilde that looks like this, we can simply rewrite the expression there. Where if you want now, instead of this expression on the singular vectors, I'm actually considering just the L1 norm with respect to this dictionary. Okay? So what I'm saying is that this term, and let me just remove this for now, can be written as x tilde w minus y hat square. Okay? This is the reason, this calculation that you just remind me how to do, is the reason why in the rest, from now on, we're just going to use this notation and work with the data matrix. But having in mind that if you want, instead of working with the data matrix, you want to work with the general dictionary, you just have to do this change of notation. Okay? Is this clear? Okay. So, any doubts about this? I can go over this once again because otherwise I just want to keep on going. Okay? Okay? So, yes?
Can you remind me again, the inner product you actually just erased, how does that reduce back to L1 norm?
It is just an L1 norm, right? So so this is for a general dictionary. But suppose that now I give you not a general dictionary, but I give you an orthonormal basis, right? Then I can ask you a more precise question, which is what is this Wj? Okay? So suppose that now we are in the special case where this function looks like this. Let me just do it in 2 steps. So this is the general dictionary case. Now let's work in the special case where we have a W. So this is, we want to take linear functions, but I want to, I want to take a specific basis. Okay? Which one? The eigenvectors. Okay? Then what I claim is that I can also rewrite this as follow. Vj Vj, okay, and then Vj x. Well, in this case it's complicated, but let's see. So I have to do the change of basis. So to write this. Okay, so I just go in here, change the basis, express this in the basis of the Vj, express that in the basis of the Vj, get this coefficient, and then I would still get the inner product of Vj, Vi, Vj, but that's just one on the diagonal because they are orthonormal. And then you get this, okay? This thing here is just the change in notation we did before, okay, for the x tilde. And this one here, now if you take the L1 norm of this, is exactly what I wrote before, is exactly what I wrote before was that we were taking this, okay? In the previous case, we were taking just what I just deleted that you wanted to see again is just this. But this is just the L1 norm of these coefficients, okay? Which are the coefficients on the new basis. Okay? Does that answer your question? Okay. So yesterday I promised you that what we were going to do, if you remember yesterday, what we did here, you notice that we somewhat starting from a filtering scenario where we make a specific choice, which is the basis to be the singular vectors, and then we justify, we introduce sparsity to a filtering perspective. Now that story doesn't hold anymore because we're not working, the filtering perspective doesn't hold anymore because we want to work with a general dictionary. And so in some sense we restarted from scratch, and instead of viewing this as a filtering of something, we just consider this as a definition, okay? And the way we derived it yesterday was by viewing this as a proxy to the so-called zero norm, okay? Do you remember what the zero norm is? You just given a vector, it counts how many vectors, how many numbers, how many entries are non-zero, okay? And if you remember yesterday, what we discussed is that it seemed that it's intuitively correct that solving the problem. I mean, first of all, we realized that solving the problem with the zero norm seems hard because this guy is not a convex function. It's a sum of indicator function, right? The one that says 1 only if the vector is non-zero. So it seems pretty nasty. And in fact, we discussed that this is as hard as doing what? Subset selection, meaning you keep a bunch of columns, you keep all, you've solved the problem for the individual columns, then all the couples, then all the triplets, and so on and forth. So you get something which is combinatorially hard. And what we argued from that perspective is this L1 could be seen as a relaxation, where each coefficient is not going to count 1, and then you sum up. What it counts is its size, okay? So clearly here there is an underlying intuition that in some sense you might want the phi j, the measurements, to be normalized, okay? Because if they're not normalized, the size of the vector doesn't mean anything. Make sense? I can always make a vector big or small just by multiplying the features by a big or small constant. So in some sense here, once you want to use this, you should have in mind that the dictionary can be pretty wild, at least for now, but if you want to look at their size, the elements should be normalized, okay? So this is where we were left yesterday. And what we wanted to do, what I promised you to do, is somewhat to give a bit of an intuition of why this is actually better at capturing sparsity than this. That's kind of where we were left. And I decided that we're going to postpone this to next Monday, because otherwise I have to give you too many different kind of ideas. What we're going to do today is instead just, we're still going to justify why L1 is a good idea from a sparsity perspective, but not relating it to L0, but only by telling you wanted to know that, by telling you how you're going to compute the solution of this problem. Okay? So in the special case where the basis is the SVD, I told you that that's an exercise. You basically have to just compute the left and right derivative of something. Here we're going to work in the more general scenario where the phi 1, phi j are not orthonormal, okay, according to some inner product. They're anything. And we want to know how to solve this problem. Okay? We will see that, interesting enough, we get something which is not as nice as this, but it's nice. Okay? It's going to be something relatively nice. So the question from the next hour or so is going to be, how shall we compute the minimizer of things that looks like that one there? How would you do it? Yeah. Fancy. Maybe. What else? I mean, what is this? What do you feel like doing? This functional, or let's say, assume that you've attended this course so far. Is there an algorithm that you can apply to solve this? Okay, that's the one that you feel like doing. Maybe it's not a good idea, and the next hour is going to explain you another method that is actually the state of the art. Okay, but subgradient is probably pretty easy, right? Because this functional is continuous, it's convex. Notice that it's not strongly convex in general. Okay, if you look at the Hessian of this stuff, well, this guy here is not strongly convex. It's just a convex. And what you see here, if you compute the Hessian of this to check strong convexity, is that it will depend on whether this matrix is invertible. So in all these situations where the matrix X, or if you want X transpose X, is not invertible, the smallest singular value is 0, then this whole thing is not strongly convex. Okay. So we still have that a solution exists because the functional is still coercive, it is convex, so we know that it's a minimizer, but we don't know that it's unique. Okay, so keep it in mind that at least for now, by solving this problem, we're going to look at the solution. We're going to look at a solution. Okay? If you do the subgradient, then the first part just reduces to the usual gradient, and the second part is just the sum of absolute values. So all you have to do is go in and compute the sum of the absolute value. So that's relatively easy. Okay? Now, it turns out that if you do that, I kind of skip the proof and of the convergence of the subgradient. I find those proofs not particularly exciting to look at. You essentially use convexity a bunch of times. But I put it in the notes, so you can look it up. Okay? And basically what you find out is that if you use, let me call this functional, this whole thing, T of W, okay, the sum of the two terms, then you basically find out that you can prove that the subgradient, which is some iteration that depends on k, if you let me call a minimizer of this functional W star, then you have that this stuff is essentially proportional to the way you initialize and how far is this from W star. I think I put it down. I think here there is a square, if I remember correctly. And up to constants, this is the basic behavior, okay? So you get a convergence rate, which is order square root of k if you do the subgradient, on the function values, not on the w's themselves, okay? Again, I skipped this proof, but it's like a half page. It's not hard to prove. And the way you have to do this is that if you remember the iteration, do you remember how the iteration of the subgradient looks like? So it's wk plus 1 equal to what? Subgradient. What? Usually is minus a gamma, and then an element, say v. Let's call it vt, which is in the subgradient. Okay, this is the notation of the subgradient of t evaluated in wt. And if you remember what I announced without proving, but again, it's the same proof that gives you this convergence, you need to put a gamma here that will decay with the number of iterations. So you cannot just put a constant, but you need to put a decrease in sequences. And the sequence should decrease fast, but not too fast. Okay? And let's say 1 over square root of k is kind of the default choice. Okay? Square this? No. No, I think that's square. I mean, that's essentially what you need to do. Okay? Yeah.
You removed k and t.
Yes. That's not my fault. It's the fault of my collaborators. I had the whole notes written with T because that's typically what you do in learning, and K is kind of what you often doing optimization, so now I have a complete mix-up, and so my brain is mixed. So when you see T and K, please let me know and just think that they're the same. Okay? So this is subgradient, just to remember what subgradient is, okay? And here, we don't do it. You can do it, or maybe it will be some exercise. Go in and tell me what the subgradient is of this function, okay? You can do it with the elementary reasoning.
Step size should be 1 or 2.
I think it's, let's see, no, this one I didn't check, so I think this should be summable, but not, quadratically summable, but not summable. So you should have that, basically gamma k square should be less than infinite, and gamma k should go to infinity, right? So something between square root of k and 1 over k would be what's good, okay? A bit more than square root of k. Fair enough, but the main point of this is not the exact choice. We're not going to play the game, what we want to say, and we're also not going to try to improve the subgradient, which is something you could try. Here we're just going to notice that, first of all, this is a general method, and it doesn't really look at the specific shape of T, okay? Nowhere we are exploiting the specific form of T. We're just taking the subgradient. If I had just one function or 55 or whatever, as long as it's convex, I can use that. I get this kind of rates, which are worse than the one you get for the gradient, okay? If you do gradient descent, you remember, anybody of you knows what's the rate you get if the function is differentiable? Or maybe just if you remember, we never talked about it. Anybody knows? So if you could put here the gradient, okay, then you will be able to put here a 1 over k convergence. So it's much faster. It's an order, it's a square root faster, okay? And in the case of gradient descent, if you remember, you don't need to take this to be a decaying sequence. You can just take this to be a constant, okay? So for GD, you can do this. You get a rate which is 1 over k for constant step size. So what we want to see today is a class of methods that is not subgradient methods. It's for functional of this form. It exploits the specific form of the functional and allows us to get the same rate as the gradient descent and to use a constant step size. Okay? And what I'm going to show you to you is the basic vanilla version, but there's been a lot of literature on this. Okay? And so you can improve, you can show that you can further improve these rates to 1 over k squared and shown that to be optimal. But we're not going to discuss that. We're just going to give you the basic algorithm that goes from 1 over square root of k to 1 over k. Okay, so this is going to be the convex optimization interlude. And so we're going to actually step away from that perspective, or rather making it slightly more general. Okay? I'm going to consider T to be the sum of two functional. Okay? F and R. If you want here, this is going to something I mess up because sometimes I pull lambda inside of R and sometimes others. But the main point here is that you have two functionals, okay? And you should think of F as an error term and R as a regularization term. So R, we're going to make very, very mild assumption on R. So to begin with, let's assume that this is continuous, okay? Because, for example, in that case, it's true. You will see, I'll comment in a minute that sometimes it's interesting to relax a little bit the notion of continuity that we want. But for now, let's just say it's continuous. The assumption on R are going to be minimal. What are the assumption? What is the basic assumption on R in the case where R is convex? Okay? We're actually going to be a bit more, makes a few more requests on F. And many of those requests are going to be the ones that are true for the square laws, for example. So F is going to be not only convex, but also differentiable And then we're going to make a further assumption, which is kind of we made for all the methods we've done so far, gradient, descent, and subgradient, which is that the gradient should be what is called Lipschitz continuous. Notice that I can write the gradient because this guy is differentiable. So this is basically, think of it in one dimension. This says that if you take any 2 points, the derivative don't change much. Okay? So the Lipschitz condition says that if you take any function, not the gradient, okay? The Lipschitz condition says that, if you have some function, it basically means take any 2 points, look at the f's, move the point here, then the values do not change much, okay? This is what this condition says. It's a notion of continuity. It tells you how much the values of f varies when you vary x. And then this L is the maximum variation you can allow yourself. Suppose that you're in one dimension, okay, and instead of this, I just put some function fw prime minus fw. So this is one dimension. Suppose that I ask you to give me an estimate of this L. What would it be? Think of that plot. You want to know, for any interval, what is the maximum variation you get on fx. This sounds like some fairly familiar object, right? The maximum of the derivative. Okay, and indeed it turns out that in one dimension, if you take here the maximum of the derivative, you get exactly the bound you want. Okay, it might be an upper bound, but you get a bound. Okay? So far so good? Suppose that now I tell you that this one is now the first derivative. And I ask you, give me a bound here. Well, what do you have to take? The second derivative. Okay? Now, if you go in more than one dimension, things get a little bit more complicated, because now the second derivative of the gradient is not just a function, but is given by the Hessian. And so what you need to do here is that you can always upper bound this by the maximum eigenvalue of the Hessian, or if you want, the operator norm of the Hessian. Okay? And this is exactly where this, another way to see why that maximum eigenvalue was going to appear. Okay? So this is just to tell you a bit where this is coming from. So we're going to assume that notice that this doesn't mean that the Hessian is invertible, is bounded from below. It just means that it's a maximum, and that's a very mild assumption. Okay? So this is the setting we're going to consider. And you can just convince yourself, you can go back here, and you can just check that all the assumptions there are true. The reason why, and in particular, you can go in and check for the square loss, what is going to be L. But you can also plug in there, say, the logistic loss. You cannot plug the hinge loss. That one is not differentiable. Okay? You would have to extend this theory. And in fact, it's not easy to do for the specific case of the hinge loss. But for logistic, square, exponential, I'm not sure because I haven't checked. Maybe you can check. So for a bunch of loss functions, you can see that they satisfy this assumption. And then by allowing ourselves, instead of just using L1 to use any convex function, we're going to have a theory that is going to allow us to have a computational framework beyond L1. Okay, what we're going to do tomorrow is that we're going to start with L1 quickly, and then we're going to move on, and instead of L1, start to massage it into many, many examples. Okay. Let me make just one side remark. This last point, the fact that you might want to be able to take general regularizer, is very important. Has been an industry in the last few years, because regularization reflects what? When you have a learning problem, the loss function you choose according to what's your target. What about the regularization? Where is it coming from? Function space, but who gives you the function space? You don't have them. So how do you, is it coming from the data?
How much you want to constrain the function, how complicated you allow it to become.
Right, so what it says is how much you want to constrain the function, how complicated you want to allow it. So I would skip would slowly turn this into two statements, okay? How much is one story, but how much is just how big you put this lambda, okay? In a sense, I'm just taking a bit literally what he's saying. He probably meant what I'm going to say. But how you do it depends on the choice of this. For example, here we said, oh, L2 or L1. But this reflects, what I wanted to say is that it reflects the prior information we have about the problem, right? Who gives you that? Well, you choose it, Okay? It's just because you have some prior beliefs and you just try to incorporate into the problem. So clearly, being able to put here very general things would be nice. So for example, the one example we're going to look at in a little bit is, here we're looking at the case where the vector is sparse, meaning that some entries are 0. Suppose that I come to you and I say that the vector is divided in groups, just because. For example, you can say, this is a biological process, this is a biological phenomenon, like as we said yesterday, disease, which is more or less aggressive. I'm looking at the gene expression, and gene expression are divided in groups because they correspond to some kind of biological process, just to make an example. And let's make the simplifying assumption, these biological processes don't have genes in common. It means that all the genes can be divided in groups. And suppose that the question I ask you is, don't give me the genes, give me the biological processes. So what you want to do is extract the groups. Does that make sense? Can we do it in this framework? Can we generalize the notion of sparsity to encompass this kind of situation? Can we then have a computational framework to ask these kind of questions? The answer is yes to both. And then you can keep on going and say, well, why did you take the groups to be non-overlapping? Can you do it when it's overlapping? What if I tell you that the groups have a graph or a tree structure? Can you try to enforce this tree structure into the problem? And maybe the tree is something given, then maybe later on I'm going to try to do some pre-processing to get it. So this is the kind of direction we want to go from tomorrow on. Okay? What we want to do today is just allow ourselves to have a framework, computational framework, which is general enough to encompass all of this. And the key properties of these guys is going to be that this is going to be convex, but not strongly convex, and not differentiable. Okay? The key point is not that much a strong or not strong convexity as much as the fact that it's not going to be differentiable. We really want to look at L1-like stuff. Okay? Okay, so with this comment in mind, let's introduce, okay, so first one comment, okay? This comment, for most of what I'm going to say, is not going to be super important, just very locally, and it's kind of annoying, but we have to do it, okay? So this functional here, the way everybody would want to define it is just as a function from, okay, so the domain of this, okay, is going to be RD most of the time. But it actually doesn't matter if you put the Hilbert space, okay? So either one. So I'm just going to use the letter R, because H, because H. Okay? But think of RD, okay? The infinite dimensionality of this won't play any role in our reasoning. So if it's a separable Hilbert space on the real field, it doesn't matter, it's RD, okay? But and then I didn't even write it, but all my objects, typically you think of them as just functionals, right? That returns number. So it turned, and we think of them as continuous functional. In fact, strictly speaking, for what we're going to discuss next, we want to slightly extend this to allow, first of all, this to be infinite, okay? So I'm going to say a couple of things that are annoying, and then I'm going to give you the motivation, okay? So bear with me just for 30 seconds. So first of all, I want to put here infinity, allow my algorithm to get the infinite value, not the algorithm, the functional. And then instead of continuity, what I actually need is to weaken this requirement a little bit to what is called lower semi-continuity, okay? Which roughly speaking means the following. Suppose that you look at, for example, this function, okay? This is a set C, an interval C, a closed interval C. And now you want to look at the indicator function over the interval. The indicator function over an interval is a function that where you input a value says 0 if you're inside of the interval, and it says infinity if you're outside of the interval, okay? That make sense? This is my definition of the indicator function of an interval. This function here clearly takes the value infinity, right? You agree? And clearly, it's not continuous. But it has the properties that all the points around these continuity points are either close to that value or smaller, okay? They're either equal to that value or, sorry, bigger, okay? So the value here are close and there is no point in the value of the function which is smaller than the point you have there. Okay? And that's essentially, in graphic terms, what it means to have a lower semi-continuous function. So the lower semi-continuity is the property, is exactly the property satisfied by a function like this. Okay? So why do we care about allowing? So what I mean here is that now, for example, I would like to be able to take C to be some kind of convex subset, closed convex subset of H, and choose R to be the indicator function of C. Okay? If I allow myself this little generalization, that you will see, you won't really see its impact. It's for technical reason that you won't really appreciate. But you can see that clearly this function is not continuous, but it is lower semi-continuous and it takes infinity value. And the motivation is because I want to allow myself to actually be able to take something like this as a regularization. We're going to use it, okay, kind of as a tool. But why do you think that's interesting? Yeah.
Because it says E cost will be infinity if the function outside of the C.
Absolutely. And why that's interesting?
So that means you're only looking at function inside C.
Okay. Why that's it? Is that clear what he said? He said, if you put this here, basically your function is going to be, you're going to look inside of C for a minimum, because outside of C, it gets infinity. So certainly it's going to be a minimum. Okay. And by the way, we're going to assume that the function is proper, which means that somewhere is not infinity. Okay. I don't even say that, but strictly speaking, otherwise you cannot even start to ask the question. Why is it interesting to allow yourself to put this kind of indicator function? Yes, it's going to basically restrict the domain. Is that something that you've seen done before? All the time, right? When you do optimization, you do it either unconstrained or you do it constrained. When you do it constrained, you basically just take C to be some subset of vector with some property. Okay? Say, for example, that the one norm is smaller than B. Okay? So now you say, instead of solving a penalized problem, I want to solve now a constrained problem. Okay? But it's still one special case of my framework, because I'm just going to pull it up. Okay? So we're going to look at this, but in the back of our mind, we should remember that we're going to make some mathematical extension that will allow us also to look at indicator functions. Okay? Hence, we're going to give a unified treatments of unconstrained and constrained minimization. Okay? So far, so good? So let's leave it there for a minute. So the main guy, the main new object, the important guy you need to meet today is what is called the the proximity operator. Okay? Let me give you the definition, and then we just try to see what it can be. Or proximal operator. So it's an operator. So it's something that takes a vector and returns a vector. And it's defined this way. So it's associated to the a convex functional. Okay, R here is any convex functional, and is given by a minimization. Okay? So you take R, you add something that looks a little bit like a regularization term, and then you minimize over U. So this problem this functional is nice, okay, because this is convex, but this is strongly convex. So this functional is continuous and strongly convex, so it admits a minimum and it's unique. So this object is well defined. And for now, it actually doesn't look particularly familiar, does it? How many of you know what's a proximal operator? That's a good number. So what I'm going to try to convince you a little bit is that to many respects, it looks a bit like a projection, okay? A projection on something, an orthogonal projection. So it is going to allow us to generalize the notion of projection in a way that is convenient for our purposes. So first of all, take exactly R, okay, to be the indicator function of a set. Okay? What is the prox operator of the indicator function? It's just a projection on the set. Basically, this says, if you take a point outside, put it to infinity. Inside, take the closest point to you. Okay? This is exactly the definition of projection on the set, the metric projection on the set. Okay? And in the special case where that C is not only a subset, but it's a subspace, then that would be an orthogonal projection. Okay? Okay, so this is one reason why this object, at least in one case, looks very familiar. It's just a projection. Okay? We have to wait a little bit to see some examples where you can compute it. Let me show you right away how we're going to compute the solution corresponding to the minimization of this problem. Okay? Let me just do it like this. The iteration is going to be very, very simple to write. And it's going to be wk plus 1 equal wk. No, sorry. Equal wk minus gamma. As promised, we will be able to take a constant. And here, we're going to put the prox operator. Okay? Again, we need a couple more examples of the prox operator to see what it is. But let me show you first the iteration we're going to study. The iteration to compute the minimizer, or approximate minimizer of the functional t, is going to be given by this expression. So we can make a few observations, okay? This iteration decouples the contribution of the error term and the regularizer, or if you want, the smooth term and the non-smooth term. The smooth term only contributes the argument of this operator, and it's essentially, if I put here the identity, what is this? If there was no prox, what is it? Gradient descent, right? It's just gradient descent. So we do a step which is called the forward step, and this is just gradient descent. And then we do another step, which is this prox step, that is a generalization of a projection. So we take a step of the gradient, and then we project, quote unquote, to enforce the fact that we want to regularize with R. So this step is called the forward step, and this one here is called the backward step. This iteration is called the proximal gradient descent or proximal forward-backward splitting algorithm. So it's proximal because you use the prox. It's forward-backward for the reason I just told you. The splitting comes from really the fact that you are considering not any minimization, but this form of minimization, which is sometimes called composite minimization, meaning that is a sum of two terms. And here you split the contribution of the two terms. Okay? Splitting methods are the one where you have structured minimization that you somewhat split in some way. Okay? So up to now, what you should appreciate, well, let's make a few comments on this up to now, okay? What do you like and what you don't like of what I wrote so far? Aside from the way I wrote it. Yeah, so that's the first observation. I give you a minimization problem. Okay, rather, you give me a minimization problem, and I came back to you with another minimization problem. And you should complain, because you're like, oh, why was not that enough? Why do we have to look at this one? So clearly, there must be a reason, and the reason is that there are actually lots of situations where this minimization problem can be either solved in closed form, so this just become a very simple operation, or it corresponds to some optimization problem that you can still solve in an efficient way. Okay, and so even if you now have this iteration plus minimization, this can be still more efficient than subgradient. Okay, and what we're going to give an example in a minute. Long story short, all the stuff that looks like L1, most of the stuff that looks like L1, you can compute the prox in closed form. And the spoiler is that it's going to be defined component-wise by the thresholding operator. We're actually going to prove it if we have time. Okay. So at that point, what you need to do is that you take iteration, and then boom, you just you take a vector, and then you just do some simple operation on the entries of a vector. Okay, and that's just what the prox operator is going to be. So that's why we are not that worried of having replaced one minimization problem with another minimization problem. So that, though, it's the main bad sides of this story. Okay, that we're going to alleviate in a second. What is? I don't see any other major bad sides of this story. So if you, but I see at least, well, it seems that there are some good sides of the story too, right? This is, again, ridiculously simple if the prox can be computed, because this is just the first order method with a constant step size, and it's just, it reminds you of what? Something like a projected gradient, right? If the prox is a projection, that's just a projected gradient. You have a set of constraints, you do gradient descent, and each step you project back on the constraint. Here you do the same thing, even when R is not a constraint given by an indicator function, but is some other function, as long as it's convex. Okay? So that's kind of nice. And it's also nice, this fact that in some sense it decouples the contribution of the two terms. Okay? You really see that this is exploiting the shape of the functional T, unlike the subgradient method. So what we want to do is convince ourselves, well, at least give one reason. There are a couple of reasons why you can convince yourself, you can have an intuition of where this iteration is coming from. One, I think, is a bit more convincing, but it's more technical. One is a bit more of a heuristic argument, but it's less technical. So I chose the second one, but you find the first in the notes. Yes?
If you can't solve a problem in closed form, would you solve for the prox normally doing like gradient descent?
No. If you cannot.
If you cannot, like how would you go?
Yeah, I mean, there is yeah, so the question is, in many situations you can solve the prox in closed form. What about if you cannot do it? Okay, we're not going to discuss so much about this, but the long story short is, it depends on R, of course, okay? And gradient descent might not work because R is not smooth, is not differentiable. So, for example, what you can do is that you can compute the prox of the prox, okay? And so you can do a double prox techniques. And for the good news for this is that for many R, the prox associated to this problem, you could do another splitting, and so for some cases you can actually try to compute that in a good way. The results essentially shows you, now you're going to have a more complicated iteration, because you have an outer iteration, and then you have an inner iteration. But essentially the results tells you that you don't need to let the inner iteration go to convergence. You can stop before. And the accuracy, if you control the accuracy well enough, the convergence rates of the overall procedure is not going to change. That makes sense? So I'm not telling you how you do it, but I'm telling you that there are iterative ways of doing it for which you can compute an approximate solution. If you want, is like putting here an error, saying, oh, I'm not going to compute this exactly. It's going to be an error. But if the error is small enough, this doesn't spoil the 1/k rates that you could try to prove for this. Okay. In the last few years, there has been essentially two industries, okay? So in the kernel world, 10 years ago, people were trying to invent kernels and apply them to techniques. Here, for a few years, there has been two industries. One that was producing regularizers, and one that was computing the proximal operator of those regularizers. So there is a ton of literature on this. But this is like the general gist to answer your question. Okay, so as I was saying, what we want to try to do is try to see how to do the computation here. Let me first try to give an intuition where this might come from. And the idea is that what we can, is essentially that we can view this algorithm as a special case of the so-called majorization minimization approach. And this approach goes like this. You have your functional t, okay? And now I'm going to give you another functional, t tilde. Just view what I'm going to say as a kind of heuristic that supposedly makes sense, okay? I'm going to give you an upper bound. I'm going to give you a functional, which is an upper bound on this, okay, for all the u's. And it becomes tight close to w. Okay? So the idea is that what I'm going to do now is that instead of solving the problem with t itself, I'm going to take a majorization of t, and then I'm going to try to minimize that one. Okay? Of course, there must be, again, some other trick for which t tilde is nicer to minimize. Make sense? So what you can see is that for these cases, a strategy to make the minimization appears to be that of considering an iterative procedure that minimizes. So given some initialization, okay, you give some initialization, then you compute this upper bound, and then you minimize the upper bound, and then you get a new solution, and then you start again, okay? I'm not going to prove anything about this, okay? All we're going to take, does this make sense? Intuitively, this seems like a reasonable heuristic, right? It's a bit like, one can see that expectation minimization like of approaches are somewhat related to this. Here, what you do is that you take an upper bound, and then you minimize it. What you can see is that that method I wrote there is a special case of this. So there is a t tilde for which we can just write the iteration. So I'm going to call this the PFB, the proximal forward backward algorithm. We can write PFB just this way for a suitable t tilde. Okay, so we can view that algorithm as a special case of this majorization minimization approach. Make sense? So how do we do it? How do you think we should do it? We want to find t tilde such that the iteration of the PFB can be written as a MM iteration, as a majorization minimization iteration. No. Next. Well, we want to have that expression over there. It looks like this one. Okay. So we want to start from that. The that seems like a reasonable start, right? So what it just says is, well, I have this prox, but this prox is equal to that. So why don't I just plug this here, I start to have an argmin, and then let's see if there is a t tilde popping out. So let me write it, +1 equal prox r wk, no, yeah. Correct? Is that fine? I just wrote it, okay? Then here what we want to do is show that essentially we can rewrite this, showing that what you're really doing is essentially taking RU as it is, but instead find some kind of F tilde WKU. Okay, we want to show that this can be seen as related to some kind of higher order approximation of F. So this is how you do it. Look at this, okay? Take the square, and then what do you get? RU plus 1/2. I forgot the gamma. Let me just see the solution, so otherwise I get the gamma wrong. So you should get 1/2 gamma U minus WK square. Then you get the product of the Let me just get one constant right that I don't remember. I don't want to do it. Oh, because it doesn't matter. Okay. So I tell you what you have to do. You take this, you take the square, okay, you develop the square, and you get the square of this plus mixed product, and then the square norm of this, okay? Then what you do is that you multiply and divide everything by gamma. So you basically have the 2 gamma appearing here, and it disappears from here, okay? The 2 was already there. So you multiply and divide by 2 gamma. No 2 here, and there is no gamma. Okay, this you can check that it disappears. And then you have this norm here. But notice that this norm here doesn't matter because it's not depending on u. So the minimum is going to change, but the value that minimizes this expression is not going to change if I do this and actually replace it by something else, which is a constant with respect to u. Okay? That make sense? So what you can do is that you can replace this just by FWQ. We did nothing, okay? It's just boring because you have to write down the calculation. If you now look at that expression, quadratic upper bound on FWK. So what you do is that you take FW, if you take F, and now you take an upper bound by taking the first and a second order approximation kind of thing. Okay? So you upper bound this by this first order term and then this second order error. Okay? So you type, and of course, that if you can check now, we didn't change RU, and now you have that this is tight around WK. If you put U equal WK, you exactly have this property here. Is that correct? Okay.
Isn't there a factor of 2 at the last term on the right?
Here,
Yeah.
maybe. I don't know, because this one you throw away and you replace it. This term here, literally, you throw it away. because it's just a constant with respect to u, and you replace with fwk. Okay, so that I skipped the calculation because it's just multiplication and okay. But the important point is that now this become the majorization we're looking for. Okay. And so now this basically gives you the interpretation of the PFB method as a majorization minimization technique. Yeah.
It's almost the same, right? But there's an R of U that's extra, right?
The what?
The term R of U is an
Yeah, because what? So this is the F tilde of this, and then this whole thing is the F tilde is the T tilde. Okay. So if you put WK equal, if you put there WK, you get exact quality. Okay, and the other one you just increased a little bit. Okay. Super late. Notice that these are not as much. I mean, in the sense that it doesn't show you that this stuff converges, okay? And it doesn't really tell you how to compute that in a better way. It just tells you that if you want, you can interpret that method as this kind of reasonable heuristic, which is finding an upper bound and then minimizing the upper bound, okay? The other perspective, which is kind of sketched in the notes, but I'm not going to describe here, is a fixed point perspective. So you know that if you have a fixed point equation, then you can use what is called the successive approximation scheme, and you can prove that to some extent that iteration is a successive approximation scheme associated to suitable fixed point equations. Okay, but that's slightly more technical, and we're not going to do it now. So what I wanted to do next is give you one example of prox, and we want to consider the case where we want to do this, where R is going to be just the absolute sum of the absolute value, so del1 norm. Okay, we want to consider the prox where that guy is just the absolute value, so that we know exactly how to compute this, at least for the L1 case. Okay? So once we know this, we actually know at least one case where we can compute it, and then I'm not sure I will have time to show you other example, but when we're going to present a different R, I'm going to show you the analogy to this one basic case. As I said, so let me give you the end answer. The end answer is going to be that you can compute this component-wise, okay, and it is just going to be exactly the operator I wrote over there. So it's just going to be take W, take the component of W, and decrease it if it's bigger than lambda, set it equal to 0 if it's smaller than lambda, increase it a little bit if it's smaller than minus lambda. Okay? So the prox operator associated to the L1 norm is just the software operator that we already defined over there. Did I get it wrong? No, right? Almost. Almost. So before we sketch the proof of this fact, let's see what it means. Okay? This is that in the case where the basis we're considering is actually an orthonormal basis, you can write the solution of the L1 problem in closed form, and you get this expression. So you don't have to run any iteration. You can just take your matrix, do some multiplication, boom, you just get the answer. Okay? If you actually work with the generic dictionary, which is not orthogonal, the problem doesn't decouple that nicely. You have to run this iteration. you have a gradient step that mixes up all the components. But then the prox operator is still component-wise. So it's not as nice as this, where you literally, you can use matrix multiplication and do it once. You have to run an iteration where you have a gradient step that mixes things up, but then the prox operator just acts component-wise. Okay? So this also gives you an example of that, well, this step is not a big deal, right? For the L1 norm, you literally all you have to do is go in, check the examples, okay? Check the coefficients, and if they're small, you set them equal to 0, and otherwise you shrink them a little bit via this. Okay? So how do you prove this? Well, let me just give you a sketch, okay? Essentially, the proof is in 2 steps, okay? The first thing is to relate the prox, well, in fact, it's 3, of R to the subgradient of R, okay? This is the step 1. The second step is to compute the subgradient of R. And then the last step is to do some kind of go back to prox R. Okay? This is roughly speaking the 3 steps. So the first thing we want to do is to look at the definition of prox operator and write down the optimality condition. Okay? The optimality condition are arguably going to give me some connection between R and prox. So how do you do the optimality condition? If you remember, if everything was differentiable, optimality condition means take the gradient and set it equal to 0. But if it's not differentiable, but only subdifferentiable, instead of an equality, you have an inclusion. Okay? So what you have to write is that an element u is equal to the prox of some other vector v if it is a minimizer of that problem. But this means that u belongs, so that if you want that 0 belongs to the subgradient of what? Of the gradient at u, okay, plus, now I have to take the gradient of the other term, which is just differentiable. So how much is it? It's u minus v squared, so it's just u minus v, right? I would get a 2. It goes away. That's why I put the 1/2 there. And then I just get this. Okay? So far, so good? This is just the optimality condition. No. I think they are. Okay? Everybody's happy? I just wrote the optimality condition, okay? Is it fine? No. So now, let's rewrite this. And what you have is that u belong no, mess. Okay. Oops. So this is the first step. This is 1. This relates the prox to the subgradient of R. So what we're going to do is we're going to compute the subgradient, and okay, but then we need to find u. So that's why we have to invert somewhat this relation. Does it make sense? So this is giving you step 1. Then what you need to do is to compute this and then go back to v, which is what you, to u, which is what you want. So the second step, basically what you can prove is that it's very easy that the sum of the L1 norm at some vector u is actually the vector given by the subgradient of the component of okay. This is pleasing. So you have a sum of absolute value, which are each one a component, and what you find out is the subgradient, it's a vector, because it should be, and each entry of the vector is just the subgradient of a component of the sum. Okay? The proof is written in the notes. It's literally one line. Okay? You basically say, oh, if each of these guy, you just write down the definition of subgradient and say, if each of these guy is a subgradient, then this implies that this is a subgradient by summation. And here you can just take a special vector to show that this is true. Okay, so this is literally one line. So all you need to do now is to compute this. Easy, right? What is the subgradient of this? So let's do this to make it slightly more interesting. So we need to take the subgradient of W at a component J. How much is this? Help me out. Exactly, you're scooping me out though. Almost, right? You still have to do the identity. So let's do it. I want to get exactly there in 2 steps. Okay? So for those of you who don't see it right away, so first of all, let's do this. Okay? I need to take just the subdifferential of this function. This function just looks like this. So how much is this subdifferential? If W1, or if you want Wj, is bigger than 0, how much is this? You remember what the subdifferential of a one-dimensional function is? Just what? Well, it depends on where you are. So if differentiable, it's just the derivative, right? So if Wj is bigger than 0, it's just differentiable, right? So how much is the subdifferential? 1. Okay, I'm just writing it in this slightly longer form. Okay, so in this case, it means that I multiply by lambda. So this is going to be lambda. Okay, if Wj is exactly equals 0, I'm going to get something between minus lambda and lambda. Okay, anything between the first and left derivative. And otherwise, you get minus lambda. Okay? This is the super easy. So we're doing slowly just because each step is super easy. Okay? This is the first step, which is super easy. Okay? The next step, is it clear? That makes sense? What you need to do next is essentially to say, okay, actually here you also need u. You have to offset everything. Okay? You just have to offset everything. So now here you have to take, essentially, if you want to make it complicated, identity plus this W. Okay? This is the complicated way of writing it. So you have to take, you basically have to shift everything by W. So let me do it. Become plus Wj. This become plus Wj. And this doesn't become anything because Wj is 0. So it doesn't change. Okay? So because of this, I need to shift everything by this amount. So I get a plus Wj, and I have to do that. Does it make sense? Okay? So subgradient can be written in components. Components are just absolute value. And then by using this condition, what I need to do is to shift them. But now I told you what is this set. This set is all the vectors that look like this. So I want to know for which u, v is going to be in this set. So what you need to do, as somebody said right away, it looks like what we need to get is something which is exactly the opposite of this. And in fact, what you need to do is exactly to invert this relation. Let's just do it graphically because we don't have time. If you look at this function, it's not actually a function, it's a multi-valued map. So what it is that in 0, how many values it can take? All the ones between minus lambda and lambda. Okay? And then above, it looks like this. And below, it looks like this. Okay? If you now take that expression and you invert it, you just get this. Okay? So I'm just doing it step by step. So of course, this last step is a purely algebraic one. This one here is also the pure algebraic one. The one that requires just a little bit of care, but it's literally one line, is this one step here to go from the subgradient of the L1 norm to the subgradient of the absolute values. Okay? But that's as far as it goes. Okay, so what we're going to try to do tomorrow is go beyond L1, explain L1 and go beyond L1. And then what I'm going to try to do is I probably won't derive. So you can do, this is the simplest computation, okay? In general, computing the Prox operator is not as easy. And you might need some further techniques. We gave kind of an introduction in the notes. Tomorrow we're going to give you the final results and point you to what are the main ideas in the proof. But unfortunately, we don't have time to cover this. Okay?